Imagine you're holding a supposedly precision machined metal part, right?
Yeah.
You need this piece for a critical project. You've been waiting like weeks for it. But as you turn it over in your hand, instead of that beautiful mirror smooth finish you were expecting, the surface is just a complete mess.
Oh, that is the worst feeling.
It really is. It's covered in these irregular waves. There are tiny dents, weird scratches, and what look like these chatter marks just scattered all over the face of it.
Right, right.
And your first thought is, what went wrong? I mean, it looks like an obvious tool failure, like the machine just completely broke down halfway through the job.
Yeah, you always want to blame the blade.
Exactly. But the truth is actually far more mysterious than just a dull drill bit.
It's a classic manufacturing mystery. We always want to point the finger at the most obvious moving part,
Right.
the cutting tool itself.
Right.
But the surface of a machined part is really it's a permanent physical record of literally everything that happened in the surrounding environment.
Or like fossil.
Yes. It captures every microscopic flaw in the setup, the software, and I mean, even the room itself.
And that is our mission today. We are taking a deep dive into a really fascinating stack of technical sources that decode these hidden culprits behind poor surface quality in milling and CNC machining.
It's a lot to cover.
It is. It's a literal detective story told in microscopic scratches and waves. So, okay, let's unpack this. Because to figure out why we didn't get that perfect surface, we have to stop looking at the spinning blade.
Yeah, we have to look way further back.
And actually, speaking of environment, I can hear the hum of heavy ventilation in your audio background today. Are you taking this deep dive from an actual machine shop floor?
I am, yeah. I've been buried in all these technical schematics and physically looking at these machines all week.
Oh, that's awesome.
And honestly, standing right next to one is the perfect place to start our investigation. Because a good surface starts long before the spindle, the main motor shaft that spins the tool, before it even turns on.
Okay, so where do we start?
We have to look at how the metal is being held down. Workpiece clamping and positioning is secretly one of the biggest saboteurs of surface quality.
Just holding the piece of metal down. I have to admit, that sounds almost too basic. I mean, don't you just put it in a vise and crank the handle until it doesn't move?
You'd really think it's that simple, but you're actually dealing with a massive Goldilocks problem here.
Like too hot, too cold.
Exactly.
Yeah.
If your clamping force is too loose, the part shifts under the immense load of the cutting tool. And we aren't talking about the metal sliding out onto the floor.
Right.
We're talking about micro movements. You literally won't see it with the naked eye while the machine is running, but the cutter is essentially trying to hit a moving target.
Oh, I see. So if the target is constantly shifting by like a fraction of a millimeter, the path of the cut is going to be slightly jagged.
Yeah.
Which leaves those irregular wavy lines we talked about.
Exactly that. But the instinct to just crank the vise down as hard as humanly possible creates the exact opposite problem.
Wait, really?
Well, if you apply excessive clamping force, especially on like thin sheets or highly precision components, you physically deform the part.
Wait, you can bend a block of solid metal just by clamping it.
You can. And what's fascinating here is how this alters the reality of the cut through something called elastic deformation.
Elastic deformation.
Yeah. The clamp squeezes the part, bending it slightly out of its natural shape. It's microscopic, but I mean, it's there. And then the machine perfectly cuts a perfectly flat surface onto that temporarily bent shape.
Oh, wow. I see where this is going. The machine does a flawless job, but only on a temporary geometry.
Yes.
So the moment the job is done and you release the clamp, the metal just springs back to its natural resting state.
You've got it. The surface that was perfectly flat under extreme pressure suddenly warps the second the tension is released.
That is wild.
Yeah, and all those dents and irregular lines are instantly exposed. And the clamp itself isn't the only static variable to worry about, actually. We also have to investigate the surface the workpiece is resting on.
The table.
Right. A hidden danger in any shop is an uneven bottom surface.
Meaning the table the metal sits on isn't totally flat.
Or, honestly, it's simply dirty. If your workpiece is sitting on a few stray microscopic chips from a previous job, or little metal burrs, or sticky coolant residue instead of perfectly clean, stable contact points, it's not truly supported.
So there are microscopic air gaps under your part.
Exactly.
So trying to mill a perfect surface with excessive clamping force or a dirty base is basically like trying to do professional calligraphy on a wobbly table while sitting on a pile of breadcrumbs.
That is a brilliantly accurate way to picture it. And to take the wobbly table analogy one step further, If your fixture, the clamping setup itself, is weak or just poorly designed, it doesn't just fail to hold the part.
What else does it do?
It actively becomes a vibration amplifier.
Oh,
Right.
geez.
It takes the cutting force, fails to absorb it, and sends those shock waves right back into the workpiece, leaving deep, really localized chatter marks.
Okay, okay. Let's assume we've swept away the metallic breadcrumbs, right? We have the perfect Goldilocks clamping force, and our foundation is rock solid.
Best case scenario.
Right. But the moment you hit the power button, the spindle starts spinning, the tool starts moving, and we've introduced, like, intense dynamic energy into the system. It sounds like our next culprit is the invisible killer of surface quality, vibration.
Yeah, vibration is incredibly tricky. It's difficult to see during the actual machining process, but it ruins a surface in fractions of a second.
How many types of vibration are we talking about here?
There are fundamentally two types we need to isolate: forced vibration and resonance.
Okay, force vibration makes sense just thinking about the mechanics of a milling tool, because
Yeah.
the tool isn't a single blade like a knife, right? It has multiple teeth.
Yes, and every single time one of those teeth enters and leaves the workpiece, it acts like a tiny hammer blow. It creates a physical impact.
Bam, bam, bam.
Exactly. And because the spindle is spinning at a set speed, those hammer blows repeat at a very fixed, predictable frequency. That is forced vibration. If it's well managed, it just leaves very fine, regular waves on the surface that might be totally within an acceptable tolerance.
But what happens when that fixed frequency hits the wrong note? The source material describes resonance as this absolute nightmare scenario, but how does forced vibration turn into resonance?
Well, everything in the physical universe has a natural frequency, like a rate at which it naturally wants to vibrate. The machine frame, the
Right.
vise, the tool, the workpiece itself.
Okay.
If the frequency of those repeating tooth impacts happens to perfectly match the natural frequency of the entire setup, you get resonance. The vibrations compound and multiply.
Wait. It's like pushing someone on a swing.
Oh, yeah.
Like if I push at random times, the person doesn't go very high. They might even slow down. But if I push at the exact right moment of their natural swing arc, they go higher and higher with barely any effort at all.
That is the exact physics at play. The vibration goes from a tiny, manageable hum to a massive physical wave.
And the part is just destroyed.
Instantly. The surface quality goes from acceptable to utterly ruined, leaving sudden, severe gouges. And then there is a specific, self-excited vibration known in the industry as chatter.
Self-excited, meaning the machine is essentially doing it to itself.
Chatter is perhaps the most damaging form of vibration because it's this vicious cycle. It happens when a previous cut leaves tiny microscopic waves on the surface.
Okay, and then what?
Then on the next pass, the cutting tool actually follows those waves. It physically bounces off them, which creates even stronger vibrations, which then leaves deeper waves for the next tooth to hit.
Oh man, a literal feedback loop of destruction.
Yes. And you can usually hear it before you see the damage.
Really? What does it sound like?
The machine starts emitting this sharp, high-frequency squeal or whistle. It's a terrible sound. When you hear that whistle, you know your surface roughness is deteriorating rapidly.
So it's leaving incredibly dense, regular waves on the metal. So if we're trying to eliminate chatter, doesn't the physical shape of the tool itself matter? The sources highlight tool overhang, which is like how far the tool sticks out from the holder.
Right.
But is that really such a dramatic factor? I mean, if I hold a pencil all the way back near the eraser instead of near the tip, I completely lose control.
Sure.
But we are talking about solid carbide metal tools here. Does a few millimeters of overhang actually make a difference?
It makes a massive difference because of how the physics of a cantilever beam work. A tool sticking out of a holder is essentially just a cantilever beam.
Okay.
And tool rigidity doesn't drop off in a straight, linear way as overhang grows. The deflection is actually proportional to the cube of the length.
Wait, so if you double the length the tool sticks out, it's not twice as bendy, it's 8 times as bendy.
You got the math perfectly. A tiny, almost imperceptible increase in tool length creates a catastrophic decrease in stiffness.
That is insane.
It really is.
Yeah.
The industry rule of thumb is that for general milling, your overhang must stay within 3 times the tool diameter.
And for finishing?
For precision finishing, where you need that mirror surface, you have to keep it within 2 times the diameter.
Wow. That is a remarkably tight tolerance. A half-inch tool can only stick out 1 inch for a finishing cut.
Yeah.
But even if the length is perfect, what about how the tool is gripped? The sources mention this term runout. What exactly is that?
Runout is a measure of how far the tool wobbles off its true center axis as it spins. Think of a wobbly wheel on a shopping cart.
Oh, okay. Yeah.
If the tool holder isn't gripping the tool perfectly evenly, the tool spins slightly off-center. This means one cutting tooth takes a much heavier bite into the metal than all the other teeth.
Which completely throws off that forced vibration frequency we just talked about, causing instant chatter.
Right. So to fight this, high-end shops actually abandon standard mechanical chucks entirely.
What do they use instead?
They use hydraulic holders or even shrink-fit holders.
Crank fit.
Yeah, with shrink-fit, they use an induction heater to physically expand the metal of the holder, drop the tool in, and just let it cool.
Oh, that's clever.
As the metal shrinks, it grips the tool with uniform 360-degree extreme pressure. It virtually eliminates runout.
The engineering required just to hold the tool straight is incredible. I also saw a note about the tool geometry itself, specifically unequal pitch end bills. How do those fight vibration?
It's a really brilliant countermeasure. Normally, the cutting teeth on a tool are spaced perfectly evenly, say exactly 90 degrees apart, on a 4-tooth tool.
Makes sense.
But an unequal pitch tool deliberately spaces the teeth at slightly irregular intervals, say 88 degrees, then 92, then 89.
Oh, they are intentionally breaking the rhythm.
Exactly.
If the teeth aren't hitting at the exact same interval, they can't establish that perfect forced vibration frequency. They constantly interrupt the feedback loop before resonance can even build.
It stops chatter before it starts. It's so smart. And we also have to consider the environmental noise.
Like what?
Ground vibration from a heavy press, or even a forklift driving by on the factory floor. That can transmit right through the concrete, up through your perfectly clamped machine, and ruin a precision cut.
It's wild to think that a forklift driving by outside leaves a permanent physical record on a high-tech aerospace part.
It really does.
Okay, so we have a rigid clamp, we've mathematically eliminated the chatter, the floor is totally still, but we still have solid metal scraping against solid metal at thousands of RPMs. The sheer physics of that generates immense friction and intense heat.
Which brings us to a completely different domain of the machining process. The unsung heroes of cooling, lubrication, and evacuation.
The coolant.
Right. People often treat cutting fluid coolant as just a messy background detail, but it actually performs 3 distinct, highly critical jobs simultaneously.
Okay, lay them on me.
First, it cools the cutting zone. Second, it lubricates the contact between the tool, the chip, and the workpiece to reduce friction.
I want to pause on the heat and friction part because the consequence of failing to cool the metal absolutely blew my mind. The sources describe a phenomenon called built-up edge, or BUE.
Oh, BUE is fascinating and highly destructive. If the cooling is insufficient and the friction spikes, the temperature in the cutting zone just skyrockets.
And the metal melts.
Basically, the workpiece material actually softens, and under the immense pressure of the cut, it essentially pressure welds itself to the cutting edge of the tool.
So the tool gets permanently coated in the exact metal it's trying to cut away.
Yes, you completely lose the razor-sharp geometry of your cutting tool. Instead, you have this messy, irregular blob of welded metal trying to scrape away the next layer.
Yikes.
It tears up the subsequent surface, leaving deep, random, cloudy marks.
Okay, so the fluid keeps it cool to prevent welding and slippery to reduce friction. But you mentioned a third job. Evacuation.
Evacuation, yes.
If we're constantly shaving off metal at high speeds, those shavings, the chips have to go somewhere fast. If they just sit there, isn't the tool going to crash right back into them?
That is known as chip recutting. If the metal shavings aren't aggressively flushed out of the cutting zone by the fluid, the tool simply plows into them again.
Which sounds bad.
It's awful. It drags these hardened, jagged little chips across the freshly finished surface, leaving random, unpredictable scratches everywhere.
Which tells me that the type of fluid you use has to be perfectly matched to the material. You can't just use a generic fire hose of water for everything.
Exactly. The chemistry of the fluid has to match the thermal and mechanical properties of the specific metal.
Like, give me an example.
Aluminum, for example, loves oil-based or vegetable-based fluids to achieve a mirror finish because they provide high lubricity. But tough materials like stainless steel or titanium demand what we call extreme pressure fluids.
Because they get hotter.
Because the friction and heat they generate will simply burn off standard oils.
Here's where it gets really interesting to me. The source notes that cast iron is often machined completely dry, or just with a blast of compressed air. I always pictured coolant as a mandatory requirement to keep things from melting. Why would you machine cast iron without it?
If we connect this to the bigger picture, It's about understanding the chip formation. Cast iron chips don't come off in long, curly ribbons like aluminum does.
How do they come off?
They break off into a fine, granular powder.
Oh.
Yeah. If you blindly spray liquid coolant onto cast iron powder, you create a thick, industrial sludge.
Oh, I mean, it just turns into industrial mud.
Literally. It clogs the machine, it packs into the tool flutes, and it completely ruins the surface finish. Air blowing is the required strategy to simply blast the dry powder away before the tool hits it again.
And when you are using liquid, how you deliver it seems just as important as what it is. Because if you just point a hose generally at the spinning tool, the fluid might just bounce off the spinning air barrier around the tool and never reach the actual cut.
Fluid spray direction is critical. If your coolant nozzle is aimed at the outer edge of the part, it's doing nothing.
So what's the solution?
The gold standard to solve this is called through-spindle coolant.
Through the spindle.
Yeah, the machine literally pumps the high-pressure fluid directly down the center of the rotating motor shaft, right through the hollow center of the tool itself.
Oh, wow.
It shoots it at tiny holes right at the cutting edges. It guarantees the fluid hits the exact point of tool workpiece contact, cooling perfectly and blasting chips away from the inside out.
Okay, let's take a breath and look at our system so far. The clamping foundation is flawless.
Check.
The tool overhang is minimized and runout is controlled with thermal shrink fit holders.
Check.
The custom chemistry coolant is blasting right through the spindle. The physical reality is dialed in perfectly. But what about the machine's brain?
The software.
Right. What digital instructions is it following? Because even with perfect physics, a bad software strategy is going to leave marks.
We're moving from the physical realm into the digital choreography, the CNC toolpaths and machining strategies.
Right.
This is where the programmer controls how the cutter physically engages with the metal. And the foundational concept here is the step over.
Step over, which is the distance between adjacent passes of the tool, right? It reminds me of mowing a lawn. You cut a stripe, turn around, move over a few inches, and cut the next stripe.
That's a great visual.
Yeah.
If your step over is too large, like if you don't overlap your stripes enough, you leave behind what's called residual height.
What does that look like?
Because cutting tools usually have a slight radius or curve on their corners to prevent chipping. A wide step over leaves very obvious, regular grooves or ridges between the passes.
So reducing the step over and overlapping the passes more makes it smoother.
Yes.
But every time you shrink the step over, you add more passes, which takes way more time. How do machine shops find the sweet spot between a perfect surface and actually delivering the part on schedule?
It requires a really strategic sequence.
Yeah.
You never try to achieve a final surface finish while removing heavy amounts of material. You rough out the general shape quickly. Then critically, you use semi-finishing passes. This leaves a perfectly stable, incredibly thin, uniform layer of material, usually just 0.1 to 0.5 millimeters, specifically reserved for the final finishing tool.
Just a paper-thin shaving left for the grand finale?
Exactly. And for that final pass, you drop the feed rate, the speed the tool travels across the metal, down to 30% or 50% of your roughing speed.
Slow and steady.
But here's the catch. If you leave too little material for that final pass, say 0.01 millimeters, the tool won't actually bite into the metal.
Why not?
The cutting edge isn't infinitely sharp. It will just rub against the surface, generating massive heat and friction without actually shearing the metal, which ruins the finish entirely.
It's all about intentionality. Even the direction the tool moves is vital. The sources heavily emphasize that for finishing passes, you should use something called climb milling rather than conventional milling.
Yes, that's crucial.
What is the actual physics difference there? Why is one better for the finish?
It comes down to chip thickness. In conventional milling, the cutting tooth enters the metal at 0 thickness, rubbing and pushing until it finally bites in and exits at maximum thickness.
So it starts by just sort of scraping.
Right. That initial rubbing creates heat and pushes the tool away from the part. In climb milling, the tooth enters the cut at maximum thickness and shears cleanly down to 0.
Oh, I see.
It pulls the tool smoothly along the cut, practically eliminating that rubbing friction, resulting in a significantly cleaner, mirror-like surface.
That makes total sense. It shears instead of scoops. But what about the moment the tool actually touches the metal for the first time?
The entry.
Yeah. I can imagine if a spinning blade just drops straight down like a helicopter onto a flat surface, it's going to leave a scar.
A direct vertical plunge leaves a very clear, really ugly point mark. And a sudden side entry where the tool just jams horizontally into the material creates a massive force spike.
Ouch.
The machine shudders, leaving a short scratch or a deep dent.
It's like doing a belly flop into a pool versus a graceful dive. The water displacement is violent instead of smooth.
Yes, exactly. So the countermeasure is a digital programming technique. You command the toolpath to use an arc lead-in and lead-out.
Arc lead-in, what does that mean?
Instead of a straight, aggressive line, the tool approaches the cut along a sweeping mathematical curve, gradually and smoothly increasing its engagement with the metal.
Oh, so it's not even a straight line.
No, it sweeps in. The cutting forces rise seamlessly, eliminating the start mark entirely, and you program the exact same graceful arc as the tool sweeps out of the cut.
It really is a beautiful choreography, and it seems like the overall strategy has to change depending on the shape of the part, too.
For sure.
Like, if you are cutting a complex 3D shape, like a curved mold for a consumer product, you can't just use standard flat horizontal passes.
Right. If you use standard Z-level machining on a sloped 3D surface, it acts like a topographical map. It cuts one horizontal slice, drops down, and cuts the next slice.
Like stairs.
Exactly. This leaves highly visible layer marks on the sloped areas. To solve this, you switch the digital strategy to scallop machining or constant cusp machining.
How does that work?
The software dynamically calculates the toolpath to keep that residual height completely uniform across all the 3D curves. It gives you a smooth surface regardless of how steep the angle is.
So what does this all mean? We started this deep dive looking at a mysterious, wavy, scratched piece of metal.
We did.
And what we've discovered is that surface quality is the ultimate holistic system. A beautiful finish isn't just about throwing a sharp blade at a piece of aluminum.
Not at all.
It requires an incredibly stable clamping foundation that doesn't bend the metal. It requires controlling tool runout with shrink fit holders and managing cantilever physics to banish resonance and chatter.
Yeah.
It demands precisely matched coolant chemistry delivered directly through the spindle and graceful, mathematically perfect arc tool paths that shear the metal rather than rub it.
It is the ultimate exercise in controlling variables. A failure in any one of those domains, a weak fixture, a bad step over, a vibrating floor, or the wrong fluid will leave its permanent, undeniable signature on the final product.
And for you listening, even if you never operate a CNC machine or step foot onto a manufacturing floor, this is a masterclass in systems thinking.
It really is applicable everywhere.
When you are diagnosing a problem in any field, whether it's software engineering, logistics, or even a persistent breakdown in team communication, don't just look at the final point of failure.
Right.
Don't just stare at the tool mark. You have to look at the foundational setup. You have to investigate the environmental noise. You have to question the underlying software or strategy that led to that moment.
This raises an important question for any problem solver.
Yeah.
Are you treating the most visible symptom, or are you actually addressing the root cause hidden in the setup?
Which leaves me with a thought I just can't shake. If a microscopic metal shaving hidden under a workpiece or an imperceptible vibration from a truck driving by outside the building can completely ruin a highly engineered manufactured surface.
Yeah.
It makes you wonder, what invisible vibrations or hidden ships are currently throwing off the precision in our own daily workflows and decision-making processes?
Now that is a thought worth taking back to the shop floor.
Until next time.